Hello everyone and welcome on today's video. My name is Wouter Perin and I'm the founder and main developer of GHEtool Cloud. And today we're going to continue our discussion on the thermal behavior of borefields. So we started this discussion last week when we were talking about how this temperature profile came to be. Now if you have not watched our last video or the video on how to interpret these temperature profiles, they are both linked in the video description below and they will help you understanding this video. So as a recap, what you can see here, it's a temperature profile in function of time, in this case 20 years, where you see three different lines. You have the fluid temperature, the average fluid temperature during extraction, so when the building is heating, and the blue line is when the building is being cooled, so we're injecting the heat into the ground. And the third line is not that visible here, it's actually the borehole wall temperature, so the temperature at which everything starts, and is the temperature of the ground at the interface of our borefields. And it lies exactly underneath these curves, and it heats up in summer when there is heat injected in the ground, and it cools down in winter when the heat is extracted from the ground. So we can also have a temperature profile that looks like this, and here the difference is clearly visible. So here we have assumed that there is cooling in every month of the simulation period, so we're injecting heat into the ground in every month, so we can see a clear distinction between these lines. And last time we said, well, this thermal behavior can be categorized in the short-term behavior in the order of hours, and it was, as we saw last video, it has to do with the effective borehole thermal resistance, the number of U-tubes, the mass flow rate, the ground thermal conductivity, and also the power. So in every month we're exchanging a certain power with the underground, and this power combined with the effective borehole thermal resistance determined the difference between the fluid temperature and the ground temperature. Now for the short term, this ground temperature is assumed to be constant. But of course, as you can see, it varies over a seasonal time scale, but also over the years. In this case, the ground cools down. And this long-term behavior is hence really important to understand, because in the end we're sizing our borefields so that our fluid temperatures are staying between certain limits. But this comes down to understanding how the borehole wall temperature evolves over time. And that's exactly the topic for today's video. So trying to answer the question how the borefield evolves thermally over time, it's solving a three-dimensional transient heat diffusion equation, which is extremely complicated. Because you have the thermal interaction between the different boreholes, which is important, and also every borehole is also interacting with the infinite ground. So the heat exchange does not stop at the boundaries of your project. No, it continues in the ground, and this interaction is also really important. And in 1987, a guy named Eskilsson developed in its PhD dissertation the concept of a G function, which is a ground response function. It's actually dimensionless, and it answers the question how the borehole wall temperature evolves over time under a constant load. And you can see it actually on the graph on the right, where you have a time scale in days. And what you can of how you should interpret this graph is actually, okay, we have a certain borefield and we're now injecting 1 kilowatt of heat into the ground constantly throughout the years. How does the ground or the borehole wall temperature evolve? And as you can see, in the beginning, the ground or this G function is really steep. And that's because, as you can understand, when you're just starting injecting heat into the ground, the temperature rises very rapidly because there is not so much ground around the borehole that's already, let's call it, thermally activated. And the longer you're injecting heat, the more the heat also spreads in the ground, and the more area is influenced by our borehole and by our bore field. So the longer we are injecting heat, the more ground is activated, let's say, the more the ground around the boreholes are activated, and and the borehole wall heats up less and less. It will forever keep increasing in temperature, but always at a slower pace as before, because there is more ground that has been activated thermally. So that's the concept of this G function. Now, how can we influence this G function? Now, the G function depends on a couple of parameters. First of all, the spacing between the boreholes. If we have a bore field where the boreholes are separated 6, 8 or 10 meters, this will have an influence on how this G function behaves in the long term. And this you can see on the figure on the left. So as you can see, the figure or the line where the boreholes are separated 10 meters is the lowest. So this means that when you're constantly injecting heat into the ground, this bore field will heat up less than the one where the boreholes are separated 6 and 8 meters. And this is of course due to the fact that the more the boreholes are separated, the more of this infinite ground they can rely on, they can thermally activate, and hence the borehole wall temperature will not increase that much as when the boreholes are closer together. And as you can see, the closest situation here, the 6 meters, it heats up the most. Now what's also interesting is that in the beginning all lines converge. And that's because at the shorter timescales, 1-2 months, the spacing is not that important, because every borehole individually takes part of the heat injection, and it heats up the ground around the boreholes, but it takes some time before the boreholes can see each other, let's say, in the ground. So after a couple of months, you can see that the situation where the boreholes are 6 meters apart, they diverge, and that's because the boreholes have already found each other thermally under the ground. So when they found each other and the thermal activated regions interact or touch, the whole bore field or the borehole wall temperature will increase faster. And as you can see, the 8 meters diverges a little bit later. And the same reasoning can be made with the configuration. So if you're placing your boreholes on a line, it's easier for them to exchange heat with the infinite ground when compared to the situation where they are in a rectangle configuration. So if your boreholes are placed in a 3x3 grid in a dense rectangle, you can see that the borehole wall temperature increases more than if they're all on one line. And this is, for example, important when you're talking about the effect of the imbalance. So if you're placing your boreholes on a single line, the bore field can handle better the imbalance because the ground heats up less over time. So the long-term effect is less pronounced when the boreholes on one line, because they can exchange heat easier with the environment. Now, if you're really looking for storing heat, so keep using the bore field as a STES, as a seasonal thermal energy storage. What you want is a bore field with a dense configuration where it's in a packed grid, and also with small spacings in between them. So the heat is really captured there. And also, of course, the ground conductivity plays a role, because if you have, as we discussed previously when we were talking about the ground properties, if we have a ground with a higher conductivity, the heat is easily transferred, and also this effect in the long term will be less pronounced. So now you can say, okay, this is interesting, and we have just one time step, or should I say one unit step. But of course, we're not always injecting heat into the ground and not always at the same pace. So how do we go from this unit step towards a real temperature profile? And that we can do by something which is called thermal superposition. So what you see here are three different graphs. So let's start at the left. And this is actually the heat load on our bore field. So you can see the first 20 hours, let's say, it's 1. The next 20, it's a half, and then it's minus a half, and then it's 0. So this is for the first 100 hours the load of our bore field. So what we then do is we separate, or we decompose this load into different unit steps. So we say, well, okay, we start at time 0 with a load of 1. So at time 0, we start here with a dotted line of 1. And then after 20 hours, we need to go from 1 to a half in heating load. So the way that we do that is we keep the load at 1, but after 20 hours, we add minus a half. So we add another unit step, this time of minus a half, so that together, and this 1 and this minus a half, they will get you this 0.5 heating load. Now the same later, so from 40 to 60 hours we have minus a half, and we come from a half. So what we do is we subtract another 1. So at time interval 40 we start another unit step, this time with a load of minus 1, so that together we have 1 minus 0.5 minus 1 together is this minus 0.5. And then again, going back to 0 means that we need to add 0.5 there. And that's the way we decompose our loads. So whether you're working with monthly or hourly loads, we always decompose it like this in the backend of the software. And now we have different unit steps. So we can now use the G function for each of these steps. So if we have the dotted line here, okay, we know that that's the G function. So we start here and we have the G function which goes like this. And then after 20 hours, we have another G function, but which is multiplied by minus a half, and which is actually this curve here. And then after 40 hours, we have minus 1, which is this G function. And then after 60 hours, we have again a positive G function where we inject heat into the ground, which is this line. And now in order to come up with the temperature profile or the temperature response of the borehole wall, we need to sum the different G functions, and then we end up with this line here, which is the temperature evolution of the borehole wall temperature. And this is actually what's behind our temperature profiles from before, where you see the seasonal variation, and this has to do with this superposition of different G functions. So to summarize, the long-term behavior of the bore field, it's really an energy problem, let's say. So the ground temperature changes over the season, over the years, due to the difference between injection and extraction of heat. So we influence actually the ground temperature, or should I say it, if we assume that the ground is a battery, we're charging or discharging this battery. And the important parameters that we as a designer can change are the borehole spacing, are the configuration, and also the ground conductivity. Now, the ground conductivity itself we cannot change, but the ground has different layers. So if you, for example, have a clay layer or a really bad conducting layer in the ground, it can be beneficial to drill less deep to not have this specific layer in order to have a good thermal conductivity in order to cope with your ground imbalance, let's say, for example. So this is the summary of what we talked about today. I just want to mention two final remarks. So the first one has to do with groundwater flow. So in the model we discussed today, we are only talking about conductive heat transfer in the ground. So we assume there is no groundwater flow. Because when there is groundwater flow, what you see is that you have a temperature plume. So the heat is not spread out concentrically around the boreholes, but it's shifted in accordance to the groundwater flow, and it influences everything downstream. Now this effect is also really important, but it's really hard, first of all, to measure the groundwater flow in practice and to have this type of information, but also to model. So these types of graphs are calculated with mod flow or free flow based on computational fluid dynamics, CFD calculations. There are some modifications you can make to the G function, which is called the moving line source G functions, but this is not yet implemented into GHEtool, but it will be in the future. And a last remark I want to make has to do with what's called cross G functions. So we now talked about the G function, which takes into account the thermal interaction between the different boreholes in the bore field. But of course, if you have a neighborhood and there are different bore fields nearby, they also influence each other. And this is called thermal interference. We will create a whole separate video on that topic. But we have there also the concept of cross G functions. So how one bore field influences another bore field. So it's the same mathematical concept, but it's defined in another way. And this will also be implemented in GHEtool in the future. We're still working together with the Polytechnic University of Montreal to figure out how we can define these G functions in the most accurate way. So to conclude this lecture and our two-part series, we were talking about these temperature profiles, and we now know that the effect on the long term is influenced by the ground thermal conductivity, by our borehole spacing and our configuration. It has to do with the seasonal and long-term variation. It's an energy problem. Whereas on the long term, we're actually more talking about the fluid temperatures, and the borehole effective resistance is important, which is, together with the power at the very instance, the difference between the borehole wall temperature and the fluid temperature. So I hope this lecture and the last one were clear to you, and that you now understand how a bore field behaves thermally. I need to say that this is all a really simplified way. The physics is way more complicated, and there's quite a lot of things to say about it, and if there is interest, perhaps we will create a more academic video of that in the future. But up till now, I hope you have understanding in how such systems behave. You have confidence in your sizing. If you think this video was interesting, please consider sharing it with your colleagues. Please consider subscribing to this channel so you get notified when a new video comes out. And I hope I see you in the next video. Take care.